Hi everyone. I'm Fong Zhenhua from Materials Science and Engineering Department. Today my presentation is this article, named Validity and Reproducibility of Counter-Electrodes for Linear Sweep Voltammetry Test in Microbial Electrolysis Cells. Now let's beginning. This article be divided to 4 parts. First is the introduction, microbial electrochemical systems are new systems employing microbial electrochemical to produce bioenergy or value-added chemicals. These include microbial fuel cell, sediment microbial fuel cell, microbial electrolysis cell, microbial desalination cell, microbial reverse electrodialysis cell, microbial electrosynthesis cell technologies, etc. Among microbial electrochemical systems, microbial fuel cells generate electricity by degrading organic matter in wastewater using microbial catalyst in the anode. This technology has the potential to prevent direct fuel combustion and convert the chemical energy of organic waste into bioelectricity. And it produces green hydrogen gas at the cathode. Next is the second part, materials and methods. First is electrode fabrication. In this study, 2 kinds of cathodes were fabricated to compare cathodes with different performances. A stainless steel mesh cathode was used after treating it with flame oxidation. An activated carbon cathode with nickel powder was fabricated for the cathode LSV test, which had a high catalytic activity for hydrogen evolution reactions. The NiCSSM cathode was prepared by attaching a catalyst layer, comprising 96.8 mg of Ni powder, 300 mg of activated carbon powder, and 1 ml of PVDF binder, onto the surface of the SSM cut to a size of 7 square centimeters. A carbon brush anode was used as an anode electrode. Carbon fibers were twisted with 2 titanium rods and then treated at 450 degrees Celsius for 30 minutes in a furnace with anaerobic conditions before inoculation. Then is MEC configuration and operation. A single-chamber MEC reactor was fabricated with polycarbonate that the anode and cathode horizontally faced each other and were spaced at about 15 mm to prevent short circuits. The brush anode was inoculated with domestic wastewater having effluents of primary sedimentation and activated sludge in the MFC with an external resistance of 1000 ohms. When the current of the MFC was stably produced, the experiment was performed by switching to MEC mode. The voltage applied for the anode and cathode was 0.9 V using a power supply. The MEC was operated in 100 mm carbonate buffer solution in a fed batch mode with an external resistance of 10 ohms at 30 degrees Celsius. Next is electrochemical test. Linear sweep voltammetry, LSV, was performed using different counter-electrodes to compare electrochemical test reproducibility of anode and cathode performances. LSV was performed in a 3-electrode system. To evaluate the validity and reproducibility of LSV tests, the maximum current, Imax, inflection potential, EF, and steep slope, M, of LSV curves were comparatively evaluated. Imax is the maximum absolute value of the current in LSV. In the LSV test, the reproducibility was compared by calculating the inflection potential and steep slope. An electrode potential was measured with the AG/AGCL reference electrode. In the cathode LSV test, based on the voltage required for hydrogen production, the slope in the voltammogram at current is produced was calculated to compare the reproducibility. The small value of EF lowers the overpotential, making it more effective for catalysts to promote hydrogen production. The catalyst with a steeper slope is the more effective producer of hydrogen gas, allowing for a higher current under an applied voltage. Therefore, to compare the reproducibility of each value, LSV curves were analyzed by linear regression to obtain the values of inflection potential and steep slope. Then is statistics.to evaluate the reproducibility of LSV test results, average values and standard deviations of duplicate experiments were calculated. The standard deviation represents an absolute degree of value difference. A larger average of values had a higher standard deviation. However, the standard deviation is not suitable for comparing samples with different average values. Therefore, the coefficient of variation was used for adjusting the standard deviation that varied due to differences in average values. The coefficient of variation was calculated with the following formulation. A relatively small standard deviation compared to the average meant that the degree of dispersion was low, indicating a high reproducibility of experiments. Coefficient of variation was calculated about the maximum current, inflection potential at inflection occurs, and steep slope after passing the inflection potential in LSV tests. Then is the kind of counter-electrode in anode and cathode LSV tests. The purpose of this study was to evaluate the reproducibility of using different counter-electrodes for anode and cathode LSV tests in a microbial electrolysis cell. The anode and cathode used in the experiment were carbon fiber brush and stainless steel mesh commonly used in MECs. But to compare reproducibility, the counter-electrodes used in this study were point wire, stainless steel wire, and mesh in anode LSV tests. In cathode LSV tests, inoculated carbon brush, abiotic carbon brush, point wire, stainless steel wire, and mesh were used as counter-electrodes. Next part is the experiment results. Include anode LSV test, SSM cathode LSV test and nickel powder activated carbon SSM cathode LSV test. The LSV test is performed to measure the maximum current, which is an indicator characteristic of electrode performance in MECs. The generated current value is an important indicator of the electrochemical activity of the anode biofilm. The reproducibility of the anode LSV test may differ depending on the materials of the counter-electrodes. In this table and figure, the maximum current value of point W using point wire as the counter-electrode was 11.05 plus or minus 0.24 mA. Maximum current values of SSW and SSM using stainless steel wire and mesh as the counter-electrode were 11.11 plus or minus 0.05 mA and 12.59 plus or minus 0.06 mA, respectively. This indicates that the activity of the anode biofilm was highest when SSM was employed as the counter-electrode. This is attributed to the larger surface area of SSM compared to SSW and point W, thereby providing a broader range of active sites available for the reaction. In Figure 2, the coefficient of variation of the maximum current was the lowest for SSW, 0.45%, followed by that for SSM, 0.48%, and point W, 2.17%. SSW and SSM had 79.2% and 77.8% lower CV than point W, respectively. The reproducibility of the anode LSV test was high for SSW and SSM. It is presumed that this is because stainless steel, the material of the cathode used during MEC operation, was used as the counter-electrode in the anode LSV test. In addition, research has recently been conducted confirming that platinum performs antibacterial reactions in platinum nanoparticles. Therefore, in the biotic anode LSV test, point W may not be an appropriate counter-electrode. As can be seen in last table, the slope of the LSV curve was also confirmed to have high reproducibility in SSW and SSM. However, the reproducibility of the EF at which current production starts did not follow the trend of the above results. Slope represents a factor linked to reaction rate, and EF pertains to overpotential. The trend in reproducibility seems to align more closely with reaction current and rate. Then is stainless steel mesh cathode linear sweep voltammetry test. The current value generated in the cathode LSV test is a clear indicator of the electrochemical activity of the cathode in hydrogen production. Therefore, the cathode LSV test is performed to confirm the hydrogen production performance, and the point electrode is mainly used as a counter-electrode. However, this study was performed to identify the reproducibility of the cathode LSV test when using various counter-electrodes. Therefore, to compare the reproducibility of cathode LSV tests, IB, AB, point W, SSW, and SSM were used as counter-electrodes. A cathode LSV test was practically performed without acetate filled, unlike an anode LSV. However, the reproducibility of LSV tests with acetate filled was evaluated in Figure 3. The maximum current values of IB and AB in the cathode LSV test with acetate filled were -8.79 plus or -0.15 and -7.12 plus or -0.25 mA, respectively. The maximum current value of point W using point wire as the counter-electrode was -7.96 plus or -0.16 mA. Maximum current values of SSW and SSM using stainless steel wire and mesh as counter-electrodes were -7.15 plus or -0.19 and -6.53 plus or -0.23 mA, respectively. The highest maximum current observed in IB can be attributed to its function as a catalyst in the biofilm, unlike other counter-electrodes. In this figure, the CV of maximum currents was the lowest for IB, 1.76%, followed by that for point W, 2.01%, SSW, 2.72%, AB, 3.43%, and SSM, 3.44%. IB had 12.4% lower CV than point W. In addition, it showed 48.6% lower CV than AB without biofilm. With acetate filled, cathode LSV test results using an inoculated carbon brush as a counter-electrode showed that both maximum current and reproducibility were high. In addition, since it was filled with acetate, it is assumed that the reproducibility is high due to the biofilm activity of the inoculated carbon brush. However, the reproducibility of EF and slope was high when stainless steel was used as a counter-electrode. To compare reproducibility from each counter-electrode more accurately, the cathode LSV tests were performed without acetate filled. In this table, the maximum current value of IB and AB was -8.87 plus or -0.15 and -6.19 plus or -0.17 mA, respectively. The maximum current of point W was -6.07 plus or -0.07 mA. The maximum current of IB was higher than that for any other counter-electrode, similar to that in the previous cathode LSV test with acetate filled. However, in Figure 4, the CV of the maximum currents was the lowest for point W, 1.24%, followed by that for IB, 1.71%, AB, 2.73%, SSM, 3.64%, and SSW, 4.17%. Point W had 27.4% lower CV than IB. Without acetate filled, the reproducibility was high when using point wire as the counter-electrode. Point had high reproducibility because it has a high electrochemical reactivity. Then there is NICSSM cathode linear sweep voltammetry test. The addition of nickel powder as a conductive material of the cathode is one of the good ways to improve hydrogen production in the MEC. Therefore, The reproducibility of the cathode LSV test was evaluated using a NiCSSM cathode with higher activity for hydrogen evolution reaction, than stainless steel in Figure 5. The EF could not be obtained, because there was no bent part in the cathode LSV curve of NiCSSM. This demonstrates the same phenomenon as observed in previous studies. NiCSSM exhibits the characteristic of higher current generation compared to plain SSM. However, identifying the point at which overpotential can be confirmed remains elusive. The reproducibility of slope was high when stainless steel was used as a counter-electrode, followed by point W. With acetate filled, the maximum current values of IB and AB were -16.01 plus or minus 1.41 and -16.99 plus or minus 3.73 mA, respectively. The maximum current value of point W was -13.26 plus or minus 0.47 mA. The maximum current values of SSW and SSM were -13.96 plus or minus 1.27 and -13.59 plus or minus 2.02 mA, respectively. The maximum current of AB was higher than that of any other counter-electrode. However, the of the maximum current was the lowest for point W, 3.54%, followed by that for IB, 8.81%, SSW, 9.13%, SSM, 14.82%, and AB, 21.95%. Without acetate filled, the maximum current values of IB and AB were -15.73 plus or minus 1.15 and -12.44 plus or minus 0.30 mA, respectively. The maximum current value of point W was -13.11 plus or minus 0.08 mA. The maximum current values of SSW and SSM were -11.95 plus or minus 0.15 and -13.57 plus or minus 0.70 mA, respectively. The maximum current of IB was higher than that for other counter-electrodes. However, the of the maximum currents was the lowest for point W, 0.61%, followed by that for SSW, 1.21%, AB, 2.43%, SSM, 5.15%, and IB, 7.31%. Finally, part is the discussion about the reproducibility of anode and cathode LSV test. The reproducibility of inoculated carbon brush anode LSV tests was evaluated by changing the counter-electrode. The maximum current of the SSM was 13.9% higher than that for point W and 13.3% higher than that of the SSW, because the stainless steel mesh had the largest surface area. Among these three counter-electrodes, the reproducibility of the EF value was the best in point W, because point has better electrical reactivity than stainless steel. In the case of the maximum current, anode LSV tests showed excellent reproducibility when stainless steel. Then is the reproducibility of cathode LSV test. In this study, cathodic LSV tests were performed with and without acetate filling as a substrate to compare the reproducibility using various counter-electrodes. In cathode LSV tests with acetate filled, IB had the highest maximum current value, because the biofilm of the carbon brush used as a counter-electrode had high electrochemical activity. The reproducibility of the maximum current of the SSM cathode LSV test was high in IB. This result showed enhanced reproducibility for an electrochemically active biofilm. And like the anode LSV test, cathode LSV tests showed high reproducibility in the counter-electrode used during MEC operation. The substrate affected the electroactivity of the counter-electrode for the EF and slope, the reproducibility was high in SSM and SSW. The reproducibility of an ICSSM cathode was overall not good. At the end is my 3 questions are from this literature. That's all, thanks for your attention.